Okay, thank you for joining me today. My name is David Schultens, and this is an MPI meeting for the connected autonomous vehicles. And a little bit about myself. I'm a co-founder in a think tank known as Hubtropolis. You can check that out, where we're basically looking to create an environment where we can simulate and plan for future city development. So the approach that we're taking to standardization is basically to identify the components that are necessary to make a successful implementation. And what we do is source artificial intelligence modules. Those become the green boxes that we are showing here in our presentation today. The green boxes are AIMs, and each have refined the best of breed technology with standardized interfaces. And that allows them to be executed in an environment where they can continue to grow and develop with standardized APIs that allow the entire system to function with the continuous evolution of the algorithms that are contained within the AI. So we're looking to open the marketplace for components that have functions and interfaces and utilize the performance competition that exists in the marketplace and find the best of breed and integrate that technology into autonomous vehicles. So the connected autonomous vehicle, known as CAV, is basically following this model where we are collaboratively and consistently refining our models in our working groups. And the comparison of the results that happen use simulation of our use cases that we've developed. The partitioning of an AIM component conditionally requires a lot of revision and training cycles, and that's what improves the interface and allows the module to be accessed through our license framework reference that comes from the MPAI store. And those modules are continually updated as they are improved. Now, why we do this is because in the open marketplace, there's going to be necessary collaboration between different manufacturers of vehicles on the roadway. The users need to be made safe, and we have to have reliable transportation that is explainable in a way that regulators can understand it, and there can be interoperability discussions in the industry. And that's facilitated by the componentization of the CAV's edge compute ability. CAV is the ultimate edge compute because it's completely autonomous and it can go anywhere.
Right.
But what we need to do to achieve that is a standards-based component process to accelerate mass market adoption. The CAV standards have milestones in a process for communicating and moving from research into standardization into eventual deployment. And so we're inventing scenarios that define the use case in simulation and identify all of the individual stakeholders that need to be considered within that simulation. Obviously, there's going to be the passenger in the autonomous vehicle. As it navigates through the environment, it may need to respond to a traffic light or an emergency vehicle and respond appropriately. And that's going to be coordinated by the evolution of technology inside of the intersection with the bandwidth and everything that's necessary to harvest frequencies and manage the negotiated data exchange, that's going to be dependent on some kind of a roadside unit to communicate with the vehicles that have the ability, and also identify other vehicles that don't necessarily have the abilities to communicate. So the COV subsystem containing the AIMs, firstly, as I said, involve the human, and we're going through the various 4 elements that are necessary to integrate all of the other code and abilities and functionalities that are evolving out of other MPI groups, such as the speech interaction between the human and the COV. And once that you've had that interaction to engage with the map functions and decide where you're going to go, then route planning and autonomous vehicle operations need to go through various stages that we define and identify as these big blue boxes. The environment sensing subsystem, the autonomous motion subsystem, and the motion actuation subsystem all need to have standardized data interfaces to handle all the synthesis of this information, and then handle the actuation of the motion in the vehicle to get where you're going, and feedback to the information to the user interface through an avatar representation that engages with the human occupant of the vehicle. So these 4 subsystem sections that we're working on collaboratively in our group are the human to COV interaction, known as HCI, that responds to the human commands and queries, sensing the activities during travel, and activates the other subsystems required by the humans as they need things within their environment. They need to communicate with other people. Hey, I'd like to call Ed and have a conversation with Ed during this transportation session. Let's be productive together. And so then we can engage. Well, the automobile is doing what it needs to do. We can do what we need to do. So the environment that is being identified is handled, without necessarily a lot of interaction between the human and the car at that point. The environment sensing subsystem acquires all the information around the physical environment and decides how to synthesize that data from the sensors and create a basic environment representation that will allow that vehicle to do the most necessary function of collision avoidance. The autonomous motion subsystem builds a full environment representation using the external and external edge compute representations that come from other connected autonomous vehicles and roadside units. And that information will be used to automatically route plan, safely avoiding collisions, and efficiently flocking behavior to gain efficiencies like, wind resistance. There is, functions like the motion actuation subsystem, sensing and the conditions of the road, and then if there's a hazard, you might want to report that to the next vehicles that are coming down the road. Hey, I experienced loss of traction. There's ice. It's below 32 degrees Fahrenheit. This is a slick area. And that kind of information can be, opted on by the independent reception of that information from another vehicle. And that can guide the motion actuation and respond to the physical environment. So what we're doing is really digging into the separate artificial intelligence modules that'll be necessary to take these 4 areas of autonomous motion subsystem, environment sensing, motion actuation, and the human experience, and put that all together in a way that is very, personally engaging, but allows you to be productive in that environment as well, and instantiate other experiences while you're in travel and you don't have to focus on the road. Of course, the distribution of all of these individual AI modules is handled by the communication to the MPI store, and the continuous evolution of the abilities of this vehicle will be enhanced as it learns more about environments and as environments continue to change. So we're really getting into the synthesis of the environment by looking at all the individual sensors that a vehicle would have, the radar data, the LiDAR data, cameras, sound, maps, all of the information that you would need from a GNSS data source to know where you are physically in the world, and all the other objects that are physically in the world. You would then need to generate something to communicate about where these objects are relative to each other. And that is, for example, the spatial attitude generator, one of the AI modules that feeds into the creation of a scene and then gives the descriptions about the scene in visual and auditory ways that the environment data can be handled by the user and understood, what's basically happening to the degree that they need to know. And the other things are handled without necessarily engaging at that user level. It just goes straight into motion actuation. So this full environment representation fusion is going to be unique in every individually manufactured vehicle, and there will be basic functionalities that one vehicle will have and another will not. As these things evolve, the abilities of the vehicle can be communicated in between each other to find out, well, what is the most efficient way to plan my route. Definitely to go slow in the left-hand most lane is less efficient. So there would be coordination to say, well, here comes an emergency vehicle. I need to avoid this obstacle and yield the right of way. And, the vehicle could then respond to the environment in that way. The spatial attitude generation and the command interpreter are going to be very important subsystems to achieve the autonomous motion and communicate amongst each other what's happening in that environment in terms of what other objects are there and whether or not they have the capability to respond in two directions with the vehicle. So in our working group, we are developing a technical report. At this stage, we're going through the architecture of the autonomous vehicle, defining these 4 interconnected subsystems that understand human utterance. That's the human to COV interaction module. It plans a route to reach a destination and senses and builds a representation of the external environment that is the basic necessity to then engage with motion. And if it's possible to then exchange that with a roadside unit or with other COVs, the basic environment representation is exchanged through data that's standardized. And then we're able to make decisions about how to execute the route and get there most efficiently and most safely through the motion actuation subsystem. For each subsystem, this technical report is going to cover the basic functionality that's trying to be achieved by that subsystem, the requirements of that functionality with all of the data input and output that would be necessary to create a topology of all the various components that execute. These are the AIMs. For each subsystem of AIMs in the technical report, we're going to go into a lot of the IO data and the formats of the data. These are the activities that we hope we can gain more membership in as our technical report is published and we move into actual simulations and engagements with other activity groups within MPI and other standards bodies involved in the automotive industry. So we're looking forward to having more people join. I'm definitely interested in taking any questions. Come join and build the future together with us in MPI. Our website is cav.mpai.community. Thank you very much.